Right now, how can we graph these four possibilities, right? Let me right, that's correct. So we'll continue. We are still in chapter 1, introduction. We'll continue with the same topic and then we'll move on to the next chapter, right? Okay, so how can we graph them? Say the first one, continuous S and continuous T. How will it look like if you draw it? So this is T. I'll just mark some numbers. But if you have a T as the x-axis, right, and then the xt, the values of the stochastic process, if it is a continuous time and continuous state space, you'll have a, actually it will be like this, right, continuous. So no, just a pattern, right, no breaks, right, continuously the line is going. So it will be a zigzag kind of line, right? Usually you can't get a straight, nice, straight, smooth line, right? So the values will go here and there, okay? But if you, so this is if you have continuous time, continuous S. If you have continuous S but discrete time, what will happen? Now this is the time. It goes, and this is xt. I'm just using some numbers. You can use any value here, right? Now the time is discrete, so you cannot have continuous line, right? Discrete time. So in between the times, there can't be any values. But the state space is continuous. So in that case, you'll get something like this. So there can be time units, right? So the gap is that you can't connect because time values are not connected. They are discrete, right? So it will look like this. Now what will happen if you have a continuous time and discrete state space? Now what will happen? What do you think? Now time is continuous, so there should be a line, but values are discrete. So how will it look like? What type of function that you will see? Now you won't get a smooth function like this, right? It's like the discrete random variables, probability or cumulative density function. How do you draw it? What type of function will it be? that will be jumps, right? So something like this. Step functions, right? This time is continuous, so the line goes, but it will not be a smooth line because the state space is discrete. So you have jumps, right? So this is a kind of a step function. Okay. Now what will be the fourth one? That is when you have both discrete, right? Discrete T and S. Now what will happen? What do you think? Both are discrete. So time, there should be dots like this, and the dots will not be in a smooth line. So it will be in step functions like this. Right? Okay. So it will look like this. Okay. So the dots if for a single value, there are if say for this is for X, there are 3 dots. They are not connected, right? And you can't have in between dots. So it's like the step function, wherever you have the angles, you put the dots kind of, right? Okay. So this is how you can graphically represent the 4 types of stochastic processes. Okay. Right, so when you get a stochastic process with the description, you should be able to figure out for which category it belongs, right? Whether it's the first, second, third, or the fourth, right? And then depending on the time set, whether it is continuous or discrete, you can define whether the stochastic process is continuous or discrete. Okay, right. Now, one of you, can you give me examples? The examples other than what we have done last time. Give me an example for the first one, continuous S, continuous T. Think about an example. You can refer to the examples we did last time, so you can design similar examples. Just think about an example. Okay, I'll give you a one. Tell me whether it is for which category does it belong. Okay. So I'm measuring the number of rainy days during the year, say 2020. Number of rainy days. What do you think? discrete T and discrete S. Okay, so let's see. Discrete S is correct. Why? Because we are measuring we are counting, right? Number of. So XT state space, number of rainy days, right? So it can be 0 days in a year, so 365, let's say, right? 20 is that is, yeah, so 366 will be there, right? With February 29th. Okay. So state space is this much. So it will be discrete, right? What about the time set? When you say rainy days, it can happen at any day, right? So it can be a time. So your time set is any day between 1st January to 31st December, right? So it can be any day. Okay. So if I modify this a little bit, percentage of rainy days. During, let's say, 1 month. So you measure the number of rainy days throughout the month, right? So at a given time, you can count what is the percentage out of the total, how many up to that day at a given date, right? So how do you do that? At a given date, right? 1 month at a given date. So the state space will be a percentage. So that will be 0 to 100, right? So this is continuous. What about the time set now? At a given date, right? So that will be 1st of month, the 2nd day of the month, up to if there are 31 days, up to 31 or maybe 30. At a given date, right? So it's going to be any one of the dates. So it is discrete time set, but continuous state space. Okay. Right. So likewise, you can come up with different examples, right? Be very careful with how you define your S and T. Depending on that, you can decide the type of the stochastic process. Okay. So with that, I will finish chapter 1, and we are moving on to the next lesson, that is about properties of stochastic processes. Okay. So under properties of stochastic processes, we are going to look at what is an increment, How do we identify independent processes? What are the independent stochastic processes? And then stationary stochastic processes. And then the Markov property. Okay. So to begin with, first we'll discuss about counting processes. Okay. Counting processes. Now these are very familiar experiments, right? If you think about tossing a coin, it is a counting process. You count maybe the number of heads or number of tails, or number of telephone calls received per hour, number of typographical errors in a book, number of vehicles passing a certain milepost, right, per day. Those kind of experiments, you can say they are counting processes, right? And you can think about Poisson distribution for these processes, right? So, for example, you can count number of heads and tossing a coin. Let's say 100 times, right? So you count. Another example, if you count the number of telephone calls received at a telephone exchange per day, right? Number of vehicles passing a junction. Those are counting processes, right? Okay, let's take the example that we are very familiar with, okay? Since the coin head and tail, we've done it a lot. Shall we try rolling a dice? You roll a dice to count whether you get let's say even numbers, right? So when you toss a coin, you get 1 to 6. So 1, 3, 5 will be odd numbers. 2, 4, 6 will be even numbers, right? So let's say rolling a dice to count even numbers. Let's say you roll the dice 100 times. Okay. And you are doing it one roll per second, right? So if you are going to model with the stochastic processes, you have to have a time. So let's say you are rolling the dice once at every second, right? So if you want to roll the dice 100 times, you need 100 seconds, right? 100 seconds. At each second, you are going to roll the dice and you are marking whether you got even number or an odd number. And actually, you are counting the number of even numbers, okay? Now tell me, what is the state space? The state space, right? You're counting even numbers. Maybe all 100 times you never get an even number. maybe 1, maybe 2. Maximum, you'll get all of them even numbers. So that will be your state space. Okay. What will be the time set? T. So you are tossing at every second, right? First second, then excuse me, up to the 100, right? So this is also discrete. Okay. Now, since we have to look at the property of an increment, we can explain it using this counting process. So let's specify in terms of increments at each second. Okay, increment, right? So we denote an increment with the notation ZT. That will be the difference between the count you got in T and then minus T minus 1. That means the previous time, previous second. Okay, so let's say each time unit for any time unit, not only seconds, right? So T will be the, XT will be the count you have at time T, and XT minus 1 is the count you had in the previous time unit. Okay, so the difference between that is called the increment, right? So X's are stochastic processes, right? So that is, if you think about the example, rolling the dice 100 times every second. So that is a stochastic process. So you get XT, that is the number of even numbers, right? And you can count it, can be a value from 0 to 100. So XT is a stochastic process. And when you get the increment, that is XT minus 1, or if you want, you can write T plus 1 minus XT. That is also okay, right? That is the current previous, the next one minus the current one, right? But usually, since the next is not visible yet, we usually go with XT minus 1. Now this increment will form another stochastic process, right? Increments form another stochastic process. If it is a stochastic process, right? What are the values that XT can get? Think about odd and even, let's say, right? Now, if you think about an example, suppose in our example, suppose we are tossing the coin, suppose we are in the 10th second, so the 10th roll, right? 10th roll, suppose the number of even values, you got 7. Next roll is the 11th one, right? The 11th roll, what are the possible values for the number of even values? If you didn't get a 1, if you didn't get when you roll for the dice for the 11th time, if you get an even number, then your count will become 7 plus 1, 8, right? So this is actually X7, right? So your X8, sorry, this is X10, right? X10 is 7. So in between, there may be odds, right? So what will be X11? For the 11th roll, if you got an even number, it will be incremented to 8, or it will remain at 7 if you got an even number, right? So therefore, your increment will be either 1 or 0, right? So the possible increment will be increment Z11 will be X11 minus X10. So if you got an even number, you'll have 8 minus 7, so 1, right? So that is if you got an even number for the 11th roll. If you got an odd number, then you cannot increment. So still 7. 7 minus 7, 0. So EZT can be either 1 or 0. 1 is when that is the probability of getting even. Right? So this will be 1 minus probability of getting even. So in this case, it will be 0.5 and 0.5 if it is a balanced one, right? Balanced dice. So you can define your new stochastic process ZT, that is for the increments, right? So you can say this ZT is a set of IID random variables, right? So it will again be a IID random variable, right? Now, although you have XTs, these XTs, stochastic processes, and from them you develop a new one called increment, and it is also another stochastic process. But if you think about these XTs, they are not independent, right? They are not independent. Why? XT is not whether you got head or tail. It is the count, right? XT is the number of heads up to now. So all XTs are depending on the previous rolls, whether you got an odd number or an even number, right? So depending on what happened in the previous rolls, the XT value, it changes, it depends, right? So therefore, XTs are not independent at all. It's a cumulative count, right? So XT is highly dependent on XT minus 1. And XT1 depends on XT minus 2, XT minus 3 kind. Likewise, it goes all the way to the back, right? So if you want to find the probability, right? Let's say probability, we were talking about the 11th roll, right? Let's make it 10, it's easy in that case. Probability that the 10th roll equals exactly 10. What do you think about this one? Probability that x10 equals 10. Can that happen? When will this happen? Probability that x10 equals 10. When will that happen? In which situation? What is x? What is x10? Number of even values up to the 10th row. Can you have 10 number of even values? Yes, right? If all the values, when you roll the dice, all the values you got were even numbers, then your xt will be 10, right? So all the rolls, if you list, it will be all even numbers. So that is x10 equals 10. So that is possible. So there is a probability, right? This will happen when all rolls gave even values. That is 2, 4, or 6. Right? Tell me whether this is possible. At the fifth value, the number of evens is 10. Is it possible? What is the probability that this can happen? It's not possible, right? You have rolled only 5 times. So there's no way that you'll end up with 10 evens, right? The maximum you can get will be 5. So this is 0. This can never happen, right? Not possible. Cannot happen. What about this one? Probability that x10 is 10 given x9 equals 7. Will this be possible? 10th roll, the number of evens 10, but up to 9th, you have got 7 evens. So can you jump up to 10 in the next roll? No, right? Because you can get only the increments are either 1 or 0. So if you have x9, 7, the possibility for x10 will be either remain at 7, that is when if you get odd, or x10 can be 8 if you got an even. So the only possibility that x10 equals, at x given xn equals 7, only possibility for x10 is either 7 or 8. So this is also not possible. That probability is 0, right? Right? So what are the possibilities for x10 to be 10? Either x9 is 9, right? That's it, right? The only possibility that probability x10 equals 10 is x9 is 9, right? That's the only possibility. So that is how you do the increments, right? And the features of the increments, how they will look like, right? Okay. Now let's do this experiment. I just will go for 3 times, otherwise your list will be huge, right? So this is in 3 seconds. So can you write all possible outcomes? This is the first roll, second roll, third roll. You can get either odd or even, right? So can you fill it? You can have all even, first even, second even, third roll also even. That is when you get x3 equals 3, right? Then suppose first even, second even, this one is odd. Even, odd, even, odd, odd. Right? So likewise, can you fill it? Then you can have odd, even, odd, odd, odd. Even, odd, odd, even, odd, odd. So these are the possibility. 2 to the 3, there should be 8, right? Yes. Okay, so these are the possibilities you can get, odds or evens. Okay. So you can come up with the probabilities. What will be the probability that you get x1, 1. Now think about you are counting even numbers, okay? Counting even numbers. What is this probability? What is this probability? How do you explain it? First roll, the number of even values 1. When it is the second roll, number of evens 2. In the third roll, number of evens 3. When is this possible? You get all even numbers, all even values. And what is that probability? This is E. So first us we have 1, next one another even. So 1, 2, there are 2. At the third, 3 even numbers, 1, 2, 3. So x3 equals 3. So what is this probability? You have E, 1 possibility out of 8. So that probability is 1 over 8. Is that clear? Right? 1 over 8. Okay. What about this one? Probability x1 equals 1, x2 equals 2, x3 equals 2. When will that happen? First is an even, second another even, so incremented 2, and no increment, that means the third one will be O. So you have E, O, that is only once, right? So 1 over 8. So likewise, for all these 8, you can write the probability like this, right? And they will have 1 over 8. Now, what is the probability that x1 equals 1? X1 equals 1. What is that probability? How do you explain that in words? You are tossing 3 times, probability that x1 equals 1. So there's no information about 2 or 3. That means they can be any, right? They can be odd or even, doesn't matter. So that will be actually probability of getting an even value. So that is this set, right? So there are 4 out of 8, which is 1 over 2. I got one answer. Yeah, it is 1 over 2. Correct. Right? Now with that, can you find this conditional probability? I want to find probability that x2 equals 2, x3 equals 3, given x1 equals 1. Now this is different, okay? It's not just the probability, this is the conditional. Conditional probability that x2 equals 2 and x3 equals 3, given that x1 was 1. Now think about the conditional probability definition. This will be the joint, that means divide by the given one. Given is x1 equals 1. Now you have this probability, which is 1 over 8. You have this probability, which is 1 over 2. Right? So what is the answer? 1 over 4. Right? So likewise, we can calculate the conditional probabilities also. Right? So any of these values, you can find those conditional probabilities. Now, can you prepare the joint distribution for x2 and x3 given x1 equals 1? How do you do that? Using this pattern, can you construct the joint PMF, the joint distribution of x2 and x3 given x1? Let's say x1 equals 1. So you can have x1 equals 0 and x1 equals 1 both. Okay. So we looked at only one incidence, x2 2 and x3 3 given x1 1. But there can be all other possibilities. You can have x2 1, x3 1 given x1 1, right? So likewise, you can come up with these probabilities. Shall we prepare it? So what are the possible values that x1, x2 and x3 can get? So the joint distribution of x2 and x3, right? So let's put x2 here and x3 here, right? It's given that x1 equals 1. So for x2, you can either get 1 or 2. Why? 0 you cannot have because you have already got 1. for the first row. So x2 will be either remaining there or incrementing, right? x3 is the same. You may remain at 1 or 2. That is, if x2 was 1, then x3 will be 2 or x3 will be 3. Is that clear how you figure out 1 and 2 for x2 and 1, 2, 3 for x3? Okay. Right now, can you try to fill these probabilities? What is the first one? This one. Can you find this one? How do you write it? Probability x2 equals 1 and x3 equals 1 given x1 equals 1. Right, so this will be x1 equals 1, x2 equals 1, and x3 equals 1, divide by probability x1 equals 1, right? So what is this combination? x1 is even, no increment, so x2 will be odd, no increment, then so that means this is also odd. So E or O, there's 1 out of 8. This 1 over 2. So it is 1 over 4. Okay. Now try this one. What is the probability? x2 equals 1, x3 equals 2, given x1 equals 1. Now think about this one. That means first roll you got an even, so x1, 1. x2 is 1, remain at 1 means the second roll you got an odd one. So increment is 0, so still at 1. If so, can you get x3 equals and then x3 equals 2, that means you got even for the third toss, right? So what is that combination? You can write it and see x2, 1, x3, increment. So this will be even, odd, even. Again, it is 1 over 8, so 1 over 4. Okay. What about this one? x2 is 1, x3 is 3. Can that happen? First toss even, second one is odd, so no increment. Then x3 can be either remain there or 0, right? You cannot jump up to 3 from 1. Increment is always 1. So there's no way that you can get three even numbers from 3 tosses if the second one was an odd one. So this combination, it's not possible, so probability is 0. Right? So likewise, what about this one? Can you get the second one 2? That is possible when x1 is 1, x2 can be 2, but can x3 be 1? You can't go down. You can't, these are always increments, right? You can't go back. So negative 1 is not possible. So there's no way that you end up with this combination. First one even, second one x2, 2 means even, and x3 remains 2 means the third one was an odd. So that will happen 1 over 8 divided by 1 over 4, 1/4. So this is where you get first even, second even, third even. So this will be the joint density. Now you can double check whether the total probability is added to 1, 1/4, 4 times, total probability 1. Right, so the marginal of x2 is there. And the marginal of x3 is there. Right? So this is how you construct the joint distribution of x2 and x3 given x1 equals 1. Okay. Now, it all depends on the value of x1, right? If x1 equals 0, what will happen? Can you try it? So I'll give you a few minutes to figure it out. Can you construct the joint distribution of x2 and x3 given x1 equals 0? What will happen? What are the possible values of x2? Just tell me what are the possible values of x2. x2 will be 0 or 1. Yes, why? Since the first toss was the number of even value 0, that means the first in the first roll you got an odd number. So the second roll, either you can get an odd number, then it will remain at 0, or if you get an even, increment to 1. So the possibilities are 0 and 1. There's no way you can get 2, right? And about x3, x3, 0, 1 or 0 or 1 or 2, right? So you can remain in 0, or you may increment to 1, or you may increment to 2. So think about the previous situation and you can try to fill this one, right? So make sure you get the total probability at the end, right? So use the same way with the given probabilities and you can fill it, right? So you can try it by yourself as homework. Right, so that's about increments. Now I hope you have the clear idea about what an increment is. Always you add one value, you're counting, right? Counting one at a time, adding one at a time. Always it's one, right? And you can't go back. There can't be jumps of more than one, right? So with that, we can write the definition of the increment. So now you see these are stochastic processes, right? They roll over the time and the increment is a stochastic process. An increment of a stochastic process is the amount by which its value changes over a period of time. Okay. Say, for example, if we consider the coin toss problem, if you think about not the next, immediately next or the consecutive jumps, but you can have many jumps, right, in between, like this. U is greater than 0, right? So you can have, now here we always looked at the next one, x1, x2, x3, immediate next one, consecutive, right? But you can think about larger gaps, right? Like you can be 1, 2, 3, 4, and so on, right? So in that case, you can have more than one increment, right? Your incremented value can be more than one in that case. That is if you do xt my t plus u minus xt, right? Is an increment which counts number of heads appears in the time interval What is the interval now? T to T plus U. Right, so to think about this interval, and up to here. So this difference is U. Okay. Now let's think about a possible scenario of this experiment, right? 10 coin tosses, 10 coin tosses. So we are doing one toss per second. Okay. These are the time values. And suppose these are the values I got. Okay. So how do you write xt? Can you fill it? x1 equals 1, x2 is still 1, x3 is 2 heads now. Likewise, can you fill it? Did you fill it? So what is x4? 3 heads now, right? Another head. So remains at 3 because it's a tail. And this is 5. x6, another head, so increment to 4. x7, another head, incremented to 5. x8, a tail, so no change. x9 head, incremented to 6. x10 is tail, so remain at 6. So these are the xt values. If possible, we call them actually trajectories, okay? Possible pattern that you can get from 10 coin tosses. Now let's try to give some numbers. Suppose u equals 5. And t equals 8. Okay, t equals 8. 8 and 5, it's 2. Okay, let's say t equals 3. Okay. So what is that interval? T equals 3 is here, right? And if you have 5 plus 3 up to 8. So you are looking at the values from t equals 3 up to 3 equals 8. In between you have 5 points. Okay. So this means we are looking at 3 to 8. Okay. So how do you write it? Can you write out the increment xt plus u equals zt plus u equals xt plus u minus xt. So how do you write it? T is 3 and u is 5, right? T is 3, 5, x 3, right? So which means, sorry, this is z. Z 3 plus 5 means z 8 equals x8 minus x3. Can you find the value? X8 minus X3. You have the numbers. X8 is 5, X3 is 5. So you can 3, you can find the value. Right, the answer is 3. So let's see, X8 is 5, X3 is 2, 5 minus 2, 3. Right, so what does that mean? In between the time limit 3 and 8, there are 5 tosses happened, and the number of tosses that happened in between that time is 3. Right, so starting from X3, which is 2, right, up to X8, it incremented to 5. That means 3 heads has occurred. So what are those 3 heads? This one, and this one. Right? So those are the 3 heads that appeared. Okay, I think it's clear now, right? How you got it. Okay, let's try another one. Let's use the same, let's use same U with T4. See what will happen now. Again 3, let's see. So this will be within the interval from 4 to 4 plus 5 is 9. So you have Z9 equals X9 minus X4. So X9 is 6, X4 is 3, 6 minus 3. Again, it is 3. Yes. Okay. So likewise, you can, it can be different numbers, right? So both cases we got 3, but it can be different values. Okay. So likewise, you can figure out the increments and you can calculate the values and all, right? Now, from that, we can come up to another definition, independent increments. Independent increments. So in general, we looked at increments, right? Now let's see what are the independent increments. What do you think? So this is how you define independent increment. A stochastic process, let me write SP for stochastic process, okay? This is how you write a stochastic process. Is said to be, is said to have independent increments if for all t and all u. And if you take the increment, xt plus u minus xt, that is the increment, it's independent of all the past of the process. All the past of the process. So that means so what happens earlier is not affecting the increment, right? So if you can find a stochastic process for all t and all u, that means that starting from any time up to any gap, if you find the increment, and if that increment is not depending on what happened earlier in that process, right? What happened earlier in that process, then we call it an independent increment. So here's your t. This is t plus u, and s will be somewhere here, 0 to t. So s will be, cs is from 0 to t, somewhere here. So past of the process, this is the past process. This is the current, this is the increment, right? So if this increment does not change, when you change what happened here, then we call it an independent increment. Now let's see an example and see how this can happen, okay? Let's use the same, shall we use the same coin toss? It's same coin toss problem. Right? So I'll take some patterns of H and T, no need to be the same. Okay, suppose this is what happened, okay? Right, so let me define a U and a T. Okay, so let me define T to be, let's say 6 and U to be 3, okay? So that means I'm finding T6 from here, 6 plus 3, 9 to here, okay? It's 0, right? Shall we go for U4 then? Otherwise, example is not good. So I'll take U4. So that means I'm going from here, okay? Right, so tell me what is, shall we write the x values? X1 is 1, x2 is still 1, x3 is still 1, x4 is 2, x5, 2, x6, 3, x7 is still 3, 3, 3, 4, 5 heads, right? Okay, so what is, we said 10. You have 2, right? So you have x10 is 5, 5 minus 3, 2. So what are those 2 heads? These 3, right? Now, if this is an independent increment, right, what should happen? This Z10 equals 2 will not change if you change the rest. So the rest is where? The rest is this set, right? The rest is this set, the earlier set, right? So if whatever happens here does not affect the increment, that means x10 minus x62, then we call it an independent increment. So what are the possibilities? When will that happen? That means you can have these h and t values. There are 3 t's and 2 h's, right? So the only restriction is from 1 to 5, there should be 2 heads and 3 tails. But where they are happening, that doesn't matter, right? Where they occur, that's not of our problem. But there should be 2h and 3 t's, right? So if you can get a coin toss, another coin toss, so still you have this x10 minus x6 equals 2, right? So if this is even, this changes while remaining 2 heads and 3 tails, then those are independent increments. So that means this increment from x10, x6 to x10 is not affected by what happened in x1 up to x5. Okay, right? So that means you may have another one like this, T, H, H, T, T. And then you have the rest. So this is still the same, but here, now the pattern is changed, but still you have 2 heads and 3 tails, right? So still x6 equals 3 and x10 equals 5, right? So even though this one has changed, still you have 2 h values and 3 t values. So in such a situation, you say that this stochastic process is, it has independent increments, but this should happen to all t and all u, right? Now this is just an instance, just to show you give you the idea, but this should happen to all t and all u, right? If you change the u and the t value, right? If you increment, the value get changed, then it's not the correct one, right? So if you do something like this, and if you change u and t values, and then the increments are changing from this one to this one, then they are not independent increments, right? So this I mentioned just to give you an idea about what independent increment is, but according to the definition, it should be for all t and all u, right? So you should be able to change, you should be able to change these h values and t values so that for any t and any u, if you calculate the increment, it should remain same, okay? So if so, then you say it is an independent increment, okay? Right. Right. So that is the definition of the independent increments. We move on to the next definition, the stationary. First we look at strictly stationary, then let's look at the weakly stationary. Okay. Now I hope have you done time series analysis? Have you done time series analysis?
This semester, madam.
This semester, okay. So in time series also you test the stationary, right? Stationary processes and all. So time series is time series is another example for stochastic process. Okay. So we say a stochastic process said to be strictly stationary if the joint distribution Okay, so here's the definition of strictly stationary, right? So what do you see here? You have xt1, xt2 up to xtn, right? And then you have xt1 plus k, xt2 plus k, xtn plus k. So what has happened? The time values are shifted by adding a number k, right? Adding a certain number k, you shift your stochastic process, if k is a positive, to the right, if k is negative, to the left, right? So it is something like, suppose you have x1, x2, x3, and if your k is 4, you'll end up with x5, x6, x7, right? So if you do that shift, the joint distribution of the original one and the shifted one are identical, right? If the joint distributions of the original one and the shifted one are identical for all possible t values and t I plus k values, then we say a stochastic process is strictly stationary, right? So in simple words, this means the statistical properties of the process remain unchanged as time elapses, right? So if you move on from x2, x1, x2, x3 to x2, x3, x4, one by one, right? Moving to the left one by one, right? For any time gap like that, if the statistical property remains, right, over this time, over each and every time lapse, right, then we say the stochastic process is strictly stationary, right? The thing is, it's not very easy to achieve strictly stationary stochastic processes, right? So if you think about that coin toss problem, let's go back to the coin toss problem. Right? Suppose if we write, we said t equals xt minus 1. And if you take t plus 1, right? So here we said t is a stochastic process. Right? If you think about this one, right? Now in this one, you are incrementing one by one, right? Incrementing one by one. So just moving every second to the right, kind of, right? Starting from xt, then xt plus 1, to go to xt plus 2, and so on, right? So in such a situation, this is a strictly stationary stochastic process. Strictly stationary stochastic process, okay? Because always the increment will be either 1 or 0. The probability will be 50-50, right? So likewise, the distribution remains same when you go from one to the next toss, to the next toss, and so on, right? So in this example, in a coin toss problem, tossing at every second, this will be a strictly stationary process, right? But the problem, as I mentioned, it is not easy to achieve it all the time, right? Not easy to achieve. right? So therefore, we usually in practical situations, we only look at weak stationary, right? Weak stationary. So what is the weak stationary? So that means you have to look at the definition of weak stationarity. So we looked at only 3 conditions, right? A stochastic process is weakly stationary if the first thing that you have to satisfy is expected value of xt is a constant for all t, right? And then the variance, what do you think? Variance of xt is constant for all t. And the third one, covariance between xt plus k and xt depends on time lag k, but not on time t. Okay, only the time lag k. So wherever you start and end doesn't matter, right? So that means if you look at x5 to x3, x2, the time lag is 3, right? So if you look at x8, x5, k is 3. So it doesn't matter where you start or where you end. Only matter is that k, right? The lag. Okay. So now you can assume usually when you have the strong one satisfied, the lower ones will be automatically satisfied. So therefore you can say if a stochastic process is strictly stationary, then automatically weakly stationary. But the other way around, it's not always true, okay? So there can be processes which are weakly stationary, but not strictly, right? There can be weakly and both strictly, but it's not always the case, okay? But if a stochastic process is strictly stationary, for sure it will be a weakly stationary one, right? Okay, so here's an example that I have used a very common two distributions that you are very familiar with. Consider a sequence of independent random variables with following properties. So xt follows exponential, let's say lambda equals 1. If t is odd, t, okay? And xt is normal with mean 1. And variance also 1. That is if t is even. Consider a case like this, okay? Now, if you want to show that xt is a and you can have only odd or even, right? So these are with the probabilities p and 1 minus p. So if you want to check whether this is a weakly stationary process, what you have to check is for all t, ext is constant, variance of xt is constant, and the covariance depend on the lag only. Shall we check it? Right? So for odd and even cases, let's try to find the expected value. So if x is exponential with lambda 1, what is the PDF? Lambda e to the negative lambda x. So otherwise, and what are the expected values and the variances of x for this situation? For a exponential distribution with this PDF, what is the ex? We have lambda e to the negative lambda x. Expected value is 1 over lambda, variance is 1 over lambda square, right? If you write the alternative way, it's the alternative way, the theta. This is another way of writing exponential distribution, right? One is with the rate, other one is the mean. So in this case, your ex is theta, and variance is theta square, right? So anyway, either way, since lambda is 1, ex is 1, variance is 1. Here also, ex equals 1, variance equals 1, right? Now, the next one we have to show is the covariance between xt plus k and xt, whether it remains same, only depending on k, right? So how do you find the covariance? Can you try it? Can you try to find the covariance between xt plus k and xt, right? How do you find the covariance? What are the, if you know these properties, you can easily figure it out. For constants A, B, C, you have covariance xy is same as covariance yx. I hope you already know them. To find the covariance of the same, sorry, covariance of with a constant, it is 0. You have covariance ax and by. That is AB covariance x and y. So these are some properties, covariance. And if you have the covariance of the same value, what do you get? Get the x is the variance of x, right? So likewise, you can, by applying these properties here and there, you can check the third condition, right? Okay. So try it by yourself, right? See whether you can figure it out. Right. So we'll try to finish the lesson by finally doing the Markov property. So we are looking at the Markov chains later, right? So this is the Markov property. Now this is very important, right? Because we are using this idea a lot in stochastic processes. Markov property for stochastic process with continuous state space. Right. So here's the definition. A stochastic process is a defined for continuous state space. Okay. I write the whole word. A stochastic process with continuous state space has the Markov property if the following happens. So the condition is the probability that xt in A Okay, so look at this expression. What is it saying? So you have xt, a stochastic process. So this S1 is a time, okay? Remember, for t, suppose you have S1 is a time value. The value is x1. So this should be simple x. Then xs2 up to xsn. So S1 up to S2, from S1, S2 up to Sn, up to Xx. So this should be XS, right? To S, right? So these are time values, right? These are time values. All of them are less than t. What is t? T is the current state, right? So t is the current time. So the probability that xt is in the space A, given that at time s1, x is x1, at time s2, x value is x2, at time xn, x value is xn, and xs equals x, that is at time s, right? This equals probability xt in A given xs equals x, only this one, right? So what does that mean? Xt given all the values from S1 up to S, right? Whatever you have from S1 up to Sn, they are actually useless, right? So the probability Xt in A is the same thing. So this probability is same as just given Sx only, right? So all the previous values, all previous states at S1, S2, Sn, right? So everything before S, right? Everything before S, all these values are before S, right? So whatever happens before the current state, they are useless, right? So the information that you get from earlier states, uh, they are not actually affecting xt. So xt is only depending on xs. So what does that, the simple mean is the future of the process will depend only on the current state. Whatever happened earlier, that's history, right? So you don't have to use them at all. You can forget them, right? So xt is only depending on xx, that is immediate previous state, right? So you can mention this in simple terms. This means the future of, or you can use current and previous, immediate previous, so you can say future of the process can be predicted from its current state alone. That's the only thing you need without any information from the history. So if you can find a stochastic process where the next step is depending on the current step only, whatever happened earlier doesn't matter, then it's called the Markov property. Or you can say the next step depends on the current stage, or you can say the current one depends on immediate past one. Earlier ones, you don't need them, right? So the next step, the next state can be predicted from the current state, only the current state. You don't need any information from what happened in earlier states. So that is history, okay? Then you can do the same definition or repeat this definition for discrete state space, right? Markov property of a stochastic process with discrete state space. A stochastic process with discrete state space has the Markov property if now your state space is a discrete one, right? So you can write xt equals a. Same thing as previous. That is the probability xt equals a given xn equals, sorry, xs equals x, only this stage. All these previous ones, you don't need them, right? So let's finish it for all times as the earlier one. These are time points, okay? To S, and this is the current one, T is the next one, future. And for all states, A. Right? So as a note, remember that when Markov process has discrete state space and discrete time set. We call it a Markov chain. So what is a Markov chain? It is a stochastic process with the Markov property. So we can say a Markov process which has both discrete state space and the time set. Right? So we are learning about Markov chains in detail in a later chapter. Okay. So what will happen in this case is whenever the process is in, say, state I, then there is a fixed probability ij that it will next be in state J. So we can prepare matrices, right? So from state I to J, what will happen and probabilities, right? So those things we will learn under Markov chain. So the next state only depends on the current state. Only depends on the current state, right? Okay. All right. So we'll discuss in detail about Markov chains later. So, so these are the properties that special properties that you should know about stochastic processes. The increments, what is an increment? I hope you got it clearly. Then what are independent increments, right? Then we call them independent processes. And then we talked about stationary processes, both strict and weak. And finally, the Markov property. So Markov property is the most important one, which means the current state or the next state is completely depending on the current state only, right? So whatever happens in the future state, it depends only on the current state. Whatever happened in earlier states, they are useless, right? So that is the Markov property, right? Right, do you have any questions about what we did today?
No, madam.
Okay, right, fine. So I'll share the lessons with you. Next week, we will be looking at the Poisson processes, right? So Poisson processes, it's one of the counting processes. So let's look at the Poisson distribution and let's do some calculations and then apply it to stochastic processes and see how we can explain it with the Poisson distribution, right? So the Poisson and exponential, they go together, right? So it will be better if you can polish up your Poisson distribution and exponential distribution. If you can recall what you have learned under those two distributions, so be prepare with them when you come to the next class. Okay.